Good evening. It is 6 p.m., but participants are yet to join. So we'll wait for a couple of more minutes before we get started. Thank you.
Hello, Sourav.
Hey Anirudh, welcome back.
Welcome to week 4 of the live sessions of University 24 AE03 Computational Science and Engineering. I am Sourav Goswami, a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. This course is taught by Professor Ashok Dey from the Department of Aerospace Engineering at IIT Kanpur. For this week, the topics that were touched upon included a wrap-up of differential equations, a brief introduction to Fourier transforms and Laplace transforms, and perhaps a little flavor of partial differential equations. And when I looked at the assignments from this week, what I could notice is that there were some questions on ODEs, perhaps a couple on Fourier series, but most were on Laplace transforms. And given the constraints of time and the syllabus which has to be covered within this course, Professor Day did touch upon Laplace transforms, but perhaps a more elaborate treatment was necessary, or so I think. So today we'll mostly be dealing with Laplace transforms. We'll be dealing with Fourier series, Fourier transforms, and PDEs in the upcoming weeks. So let's get started. One remnant from the ordinary differential equations module was the method of variation of parameters, which we have not gone over. So we'll do that first. So say for any linear second order DE, which is given in standard form here. So it will be y double prime plus some function p of y prime plus some function q uh, times y equals fx. So it's non-homogeneous. It will have a general solution, which will consist of a complementary function and a particular solution. The complementary function is the solution of the homogeneous equation. That is when we set the right hand side of this equation to 0. The particular solution is a solution that accommodates this f of x that we have on the RHS here. And we saw that how for the solutions to be linearly independent, we may assume a particular solution of the form uh, u1, which is some function of x times y1 plus u2, which is another function of x times y2. And if we were to grind it out, you know, solve out the whole equation, substitute back, we'll find that eventually, with some simplification, the solution, so if the particular solution is of this form y1 u1 u1 y1 plus u2 y2, we can have expressions for u1 and u2. So u1 prime would equal w1 by w, w1, w, w2, they are Wronskians. We looked at Wronskians in the previous weeks, where we primarily use them to say check if functions are linearly independent, if the set of solutions of a linear equation or a system of linear equations are independent. Further, that are also defined here. Once we have u1 prime, we can integrate to obtain u1. Similarly, from u2 prime, we can integrate to obtain u2 and go back, substitute, and end up with the total solution. So first we must compute, I'll just write it here. So step one is to say compute the complementary function that will come from the homogeneous solution or the homogeneous equation. The next step is to use the complementary solution. So say for a second order ODE, you would have two of them. So maybe some C1y1 plus C2y2. Next, we use these y1 and y2 to compute the particular solution, which as we saw is assumed to be some u1 y1 plus u2 y2. And by going through this method of variation of parameters, we obtain these u1 and u2. And finally, we end up with the general solution, which is actually a linear combination of the complementary and the particular. While integrating from u1 prime to obtain u1 and from u2 prime to u2, we will be performing indefinite integrals, but will not be using or putting any constants of integration. And why that is explained here. So say in the case that we did put some, say if I did integrate u1 prime to get u1 plus some constant a1 and integrated u2 prime dx to obtain some constant b1. The way we'll go about is for the general solution, if we substitute it back, anyway, this will turn out to be a part of the existing coefficients, and then we may just simply substitute with them with some other arbitrary constant. And so, well, it does not really matter, is what it is. The other method, which was discussed in the course, was the method of method of undetermined coefficients, where say you have a few say fundamental or elementary function types such as constants or polynomials or trigonometric, even exponential. And based on the type of fx that is on your RHS, based on the type of or on the structure of the elementary functions which it contains, we start by guessing a solution, which is again of a similar sort. Maybe a table was also shared which contained these standard forms and the solutions we can guess just by looking at them. But it is found that the method of variation of parameters has certain key advantages over the method of undetermined coefficients. So I found it interesting. I'll just write it here. So the advantages of a method of variation of parameters over method of undetermined coefficients. So one is that the method of variation of parameters always, and that is a strong word, yields a particular solution YP. Of course, provided it exists or provided the associated homogeneous equation can be solved. A second is that the method of undetermined coefficient is limited to a very select few elementary function types. So it's limited to cases where the input function or fx is a combination of a few types of elementary functions. And the four types which are generally encountered are, say, constants, polynomials, then you have trigonometric functions and exponential functions. Again, VOP is not limited to ODEs with constant coefficients only. And you'll find that this method of variation of parameters has a well-defined algorithm and is more systematic. And of course, say is more rigorous than trying to guess a form of a solution using method of undetermined coefficients. And so it is generally preferable to use this. The final choice, of course, rests with you. And typically, say in some exam or even in some real life scenario, the method would not be specified. So yeah, it's totally up to you what you use. And just for the sake of completion, I have included the algorithm for solving even higher order equations using the method of variation of parameters. So for any general nth order differential equation of the standard form, first again we compute the complementary function. So it's an nth order. So the complementary function will be a linear combination of n solutions. So say the complementary function yc is c1 y1 plus c2 y2, so on till cn and yn. Then the particular solution again will be of the form u1 y1 plus u2 y2 plus u3 y3 and so on till un yn. Again, we can put them into n equations and using Cramer's rule and by first computing the respective Wronskians, we can obtain the derivatives. And for every uk prime, we can integrate it to obtain a uk, and thus we obtain our particular solution back. The Wronskians for such a third order differential equation are also supplied here for your ready reference. And anyway, we'll be solving equations, so the method will be clearer. Now, on to the Laplace transforms. So, first, I think it's best to know what a transform really is, and we have been using it without even knowing. I don't think it was ever stated to me, but say transform. So, a transform basically transforms one function into another. That is not a very helpful definition, but I'll just illustrate it. So, say you have a function x square. It's a quadratic or a second order polynomial. When I differentiate it with respect to x, I end up with 2x. Now this is linear. If I integrate x square with respect to dx, and this is the indefinite integral, I end up with x cubed by 3 plus some constant, which is a cubic polynomial. And say if I were to perform a definite integration over some interval, say 0 to 3, I'll end up with x cubed by 3 between 0 and 3. This will be 27 by 3 minus 0 or 9. This is a constant. So by performing either differentiation or indefinite integration or definite integration, I transform the given quadratic polynomial into either, say, a linear function, a cubic polynomial, or a constant. There's even differentiation and integration, whether indefinite or definite, are also transforms. They transform a function into some other type of function. And one very useful transform which helps us solve ODEs is the Laplace transform. And here is how it is defined. So for any function which is defined for t greater than equal to 0, the integral 0 to infinity e power minus st f of t dt is actually the Laplace transform, provided the integral converges. S is a parameter here, and what we are actually doing is we are transforming our function from the t space to s space. And yeah, it's evident here. So we start with the function of t, end up with the function of s, and the convention is that when we use a lowercase letter to denote the function, say if I use small f of t, I'll denote the transform by capital S, or it can be the reverse way as well. Say if I want to denote my function with a capital letter, the transform will typically be denoted by the small letter. Some theory, just to be rigorous. So the sufficient conditions for existence of a Laplace transform of any function is that the function f of t has to be piecewise continuous on the interval 0 to infinity. and it has to be of exponential order. Then the Laplace transform will exist for some s greater than c. What is exponential order is again defined here. So any function is said to be of exponential order if there exist constants c and m greater than 0, and for some t greater than 0, such that the magnitude of the function is less than equal to this exponential function that we construct, m e power ct, for all t greater than this chosen t. So it's a mathematical construction, basically to say limit the bounds which a function might reach or the value of the function might reach. So here typically we see that for this example here in figure 4.1.2, our given function f of t in blue is of exponential order for all t greater than capital T, because its magnitude is lower than m e power ct, where c is greater than 0. However, for this region where small t is less than capital T, we see that the magnitude of the function f of t is greater than m e power ct. So in this region, it is not of exponential order. Similarly, there are other examples given over here. So simply f of t equals t, which is of exponential order for all t greater than 0, greater than equal to 0. E power minus t, which is again of exponential order for all t e of for all t greater than equal to 0. So given here. And the third example is of the function 2 cos t, which is again of exponential order for all t greater than 0. I have also compiled the formulae for some basic uh, the Laplace transforms of some elementary functions. Okay, it appears the equals sign is missing here, but just in case. So the Laplace transform of 1 is 1 by s. For t power n, it is n factorial by s bar n plus 1. For e power at, the Laplace transform is 1 by s minus a. For sine and cosine, k by s square plus k square and s by s square plus k square. And similarly for sine hyperbolic and cos hyperbolic. This might prove handy, and we might need to refer to the standard formula while we are solving the equations. Again, one important property of the Laplace transforms is that it is again linear. So remember, even differentiation and integration are linear, and so is the Laplace transform. So if you want to transform a function f of t plus g of t, so the Laplace transform of this whole is equal to the Laplace of f of t plus Laplace of g of t. Again, even if you were to multiply it with some scalars, so the Laplace of say alpha f of t plus beta g of t, we can again pull the scalars out. This will equal alpha times Laplace of f of t plus beta times Laplace of g of t. And it comes straightforward from the integration and is also shown here. This linearity of the Laplace transform comes really handy when we try to find the transforms, inverse of the transforms, or in general, we are just solving, say, ODEs. And just to illustrate the methodology, we'll just compute some simple Laplace transforms here. So here we'll compute the Laplace transform of sine of 2t. So just to recollect, the definition for the Laplace transform of any function is integral 0 to infinity e power minus st f of t dt. So when we try to do this for sine of 2t, this will come out to be integral 0 to infinity e power minus st sine of 2t dt. And up front, we can see that this is the integral of products. And the way I remember it is this. So for UVDX, it will be equal to U into integral of VDX minus integral of differential of U into integral of VDX whole dx. Of course, here U and V are functions of x. Similarly, if you have definite integrals, so you have some interval in which you want to evaluate it. The way we apply the limits is we calculate this entire function and use the limits. And here again, this inner one is indefinite, and we apply the limits here. So let us choose our functions. We'll have to integrate time and again, so it's best if we choose u to be the exponential. We choose u to be the trigonometric sign and v to be the exponential. So integrating would be easier. And I just denote my integral by I. So this is u into integral of v dx or dt in this case, minus integral of differential of u, integral of v and dt. So this will simply turn out to be sine of 2t times e power minus st by minus s evaluated between 0 and infinity. And this will turn out to be derivative of sine of 2t will be 2 cos 2t. And here again we have e power minus st by minus s dt. So this is uh, sine 2t e power minus st by minus s plus 2 by s integral 0 to infinity e power minus st cos of 2t dt. Now let's look at the first term here. So when t approaches infinity, sine of 2t is still finite because its value will say always range between minus 1 and 1. And e of minus st will tend to 0. So I raise e to a very large power, but it's negative. So it'll tend to 0. And for t equals 0, sine of 2t is 0. So the entire first term will go to 0. And what I'll be left with is just the second term, cos 2t dt, or let me call it 2 by s I1. Now let's compute I1. So I1 again is an integral of product of functions. So 0 to infinity e power minus st cos 2t dt. Again, to make life easier, we'll take v to be the exponential and we'll compute this. So it will turn out to be u into integral of v dx minus integral of differential of u into integral of v dx, or dt in this case, or dt. This will come out to be e power minus st by minus s evaluated between 0 and infinity. Of course, when I write infinity here, It's not really a limit, or it is a limit, it's not really a value. The proper way to write it would be say 0 to b, where b is tending to infinity, but just for shorthand, I'm writing it this way. And this will turn out to be minus 2 sine 2t e power minus st by minus s dt. Let us evaluate the first term. So when t tends to infinity, again cos 2t is finite. Its value will always range between minus 1 and 1. E power minus st tends to 0, so the product will go to 0. And when t is equal to 0, this term will turn out to be cos 2t power minus st by minus s will turn out to be minus 1 by s. So the first term here will become 0 minus 1 by s. And the second term is minus 2 by s times 0 to infinity e power minus st sine 2t dt. And so this is 1 by s minus 2 by s. Very interestingly, we have returned to where we started. We set out to evaluate this very integral, and we are back at it. So, but it's not as bad as you think. So let me just put it as I again. So I1 is 1 by s minus 2 by s times I. Let us go back to the original equation. I was 2 by s times I1. But what is I1? I1 is 1 by s minus 2 by s times I. So I will have an equation in I. So this is 2 by s square minus 4 by s square I, or I into 1 plus 4 by s square is 2 by s square, which implies that I into s square plus 4 by s square is 2 by s square, or I equals 2 by s square plus 4, or perhaps a more useful form is s square plus 2 square. This is indeed the linear transform of the Laplace transform of sine of 2t. And in more general terms, the Laplace transform of sine of at would equal a by s square plus a square. Of course, so most of these would be available to us as a standard formula, but it helps to just go over the steps once, and it also serves as a very good, say, revision of integration. Now we have a transform, so we'll also have its inverse in most cases, and I have here compiled here some routine formula used for calculating the inverse transforms. So you'll find that, yeah, earlier we had L of 1 equals 1 by s. We just took it to the other side, put an inverse sign. But yeah, it helps to remember these things. So the Laplace transform inverse of 1 by s is 1. For n factorial by s power n plus 1, it is simply t by n, and so on and so forth. The inverse of Laplace transform is again linear, and just to illustrate the methodology, we'll quickly solve one case of inverse of linear transform. So I noticed that in the assignment for this week, there is a question where you asked to calculate the inverse Laplace transform of a given function. So I'm sure this will really help. And this also illustrates the case for, uh, say, breaking up into partial fractions or disintegrating a given function into partial fractions. So let's see how it goes. So the key idea here is that for a function of this sort, say where you already have non-repeating distinct roots, s minus 1, s minus 2, s plus 4, this can be broken into a sum of partial fractions a by s minus 1 plus b by s minus 2 plus c by s plus 4. And of course, one, say, brute force method to calculate this would be to multiply all the terms, simplify them, equate the coefficients of, say, s square, s, and constants on left hand side and the right hand side, and find it out. However, it's not the most efficient method. Perhaps a far quicker method is something known as the cover up method. And no, we are not really trying to cover up any mistakes. That's the actual name of the method. And how this works is, say, I know that s equals 1 is one of the roots for this equation. So what if I just multiply both sides by s minus 1? So I multiply either side by s minus 1 and simplify. So these will cancel out and it will survive in the other terms. Now, if I were to very cleverly put s equals 1, I notice that now this term will go to 0 and so will the other one. And so I have directly calculated one of the numerators or one of the coefficients. And this can be generalized for the other coefficients as well. So in general, we may calculate a as, say, and what we are really doing is there was this other term here, s minus 1. It's like we covered it up and put s equals 1, and that is why the name of the method. And this will come out to be 1 plus 6, 7, 16 by minus 5 or minus 16 by 5. Similarly, I can calculate b. So this is s square plus 6s plus 9 by s minus 1, s minus 2, s plus 4. I cover up the second root. So b is the numerator for s minus 2. So that is the term we'll be covering up. Evaluate this at the root. So s equals 2. And what we end up with is 4 plus 12, 16 plus 9 is 25 by 6. And similarly for C. C is the numerator or the coefficient of the third term, which is 1 by s plus 4. So we cover up s plus 4, evaluate this at s equals minus 4, since minus 4 is the corresponding root, and evaluate. So 16 plus 9 is 25, minus 24 is 1 by minus 5 times minus 6, so 30. And here we have found are three coefficients. So s square plus space. Oh, I have little space. Might as well conserve it. So s square plus 6s plus 9 by s minus 1, s minus 2, s plus 4 is equal to minus 16 by 5 by s minus 1 plus 25 by 6 s minus 2 plus 1 by 30 s plus 4. And now that we have broken it up into these partial fractions, we can evaluate it really easily. So owing to the linearity principle, we can calculate all of them individually. So this will amount to the Laplace inverse of minus 16 by 5 by s minus 1 plus the Laplace inverse of 25 by 6 by s minus 2 plus the Laplace inverse of 1 by 30 by s plus 4. Again, we can pull the constants out if they're not needed. So this is minus 16 by 5. Laplace inverse of 1 by s minus 1 plus 25 by 6. Laplace inverse of 1 by s minus 2 plus 1 by 30. Laplace inverse of 1 by s plus 4. And now we go back to the standard formula that we have, and we try to identify the form which these terms might be possessing. So they're of the form 1 by s minus or s plus something, and this seems like a good fit. I'll just write it here. The Laplace inverse of 1 by s minus a is e power a t. So the Laplace inverse that we are set out to compute. So here a is equal to 1. So e power t plus 25 by 6. Here a equals 2. So y power e power 2t plus 1 by 30. Here a is equal to minus 4. E power minus 4t. And this is the answer we are looking for. So calculating the Laplace transforms and inverse of the Laplace transform is a really straightforward exercise if we are up to date and say well versed with integration, and once we learn to identify the standard forms and remember the formulae. However, the principal reason why we are learning Laplace transforms is to be able to solve uh, differential equations. Differential equations will involve derivatives, and thus perhaps the most important is the formula for the transforms of derivatives. So for the nth order derivative fn of t, remember when we write it without brackets, it's an exponent. When we are using brackets, this is the nth order derivative. At least that is the convention we have been following. Different texts may prescribe different conventions. So for the nth order derivative, the Laplace transform gives s power n f of s minus s power n minus 1. So f of s is like the Laplace transform of f of t. This f of 0, f prime of 0, f double prime of 0, and so on till f n minus 1th derivative calculated at 0 are actually the initial values supplied to us. And thus we can see the usefulness of utilizing these Laplace transforms for the solution of initial value problems, where typically say if you have a second order, you will be supplied the values of the first derivative and the zero derivative. For a third order, So for the first order, you'll just have the value of the function. You'll typically have second derivative evaluated at 0, first derivative evaluated at 0, and the function itself evaluated at 0, and so on. And how this is helpful is that we use the Laplace transform to transform the differential equation into an algebraic equation in YS. And we'll see how that is accomplished. The general algorithm for utilizing Laplace transforms for solving differential equations is also given here. So first we form the differential equation, we find the unknown yt with satisfied d and the initial conditions. We apply the Laplace transform to either side of the equation. Now the transform differential equation will become simply an algebraic equation in YS. We will solve the algebraic equation, so it will have polynomial terms. It might involve again decomposition to partial fractions and so on. Once we have solved the equation for YS, we simply apply the inverse Laplace transform and we are back in our T space again and we have a solution for the original initial value problem that was supplied to us. Similarly, some additional theorems are given here. So just like we had transforms of derivatives, we can also compute derivatives of transforms, so to say. And these formula are to be memorized. There's not much I can do here. So the transform Laplace transform of t power n f of t equals minus 1 power n dn dsn. So the n derivative with respect to n s of f of s. Similarly, the convolution theorem, which Professor Day also touched upon in his lectures, which suggests that if f and t are piecewise continuous on the interval close 0 to infinity and of exponential order, then the convolution function f convolution g shall have the transform given by L of Laplace of f of t times the Laplace of g of t. Similarly, we also have Laplace transforms for integrals, just like we had them for derivatives. And it actually comes from the convolution theorem itself. The Laplace transform for the integral 0 to t f of tau d tau equals capital F of s by s, and the inverse again, the Laplace inverse of f of s by s will actually be the integral 0 to t f of tau d tau. And some additional theorems which might come in handy. I did not see them in any of the assignments or the quizzes, but just in case you might end up encountering, say, the Dirac delta function or the Heaviside unit step function. So the formula for Laplace transform of the Dirac delta function is Laplace, the transform of del t minus t naught is e power minus s t naught. And if we are to find the Laplace transform of any periodic function which has a period t greater than 0, then it's also given here. So the Laplace transform of such a function will be 1 by 1 minus e power minus st integral 0 to t e power minus st f of t dt. Okay, that's a summary of all the theory which was covered this week. Next, we'll solve some illustrative examples, but for now, we'll break. Say we'll resume at 7:05. Welcome back. Let us resume and look at some problems. So first, we'll solve a couple of ODEs using the method of variation of parameters. And here is one that is given to us. So y double prime minus 4y prime plus 4y equals x plus 1 e power 2x. So it's a non-homogeneous ODE, and we know that the general solution shall consist of the complementary function and the particular solution. So our first step should be to find the complementary function yc. Yc is calculated or computed for the homogeneous equation. So y double prime minus 4y prime plus 4y equals x plus 1. Sorry, the RHS will equal 0, and we go the usual route. So we assume a solution of the form e power mx e power lambda x, anything, and substitute it back. So this will give y prime equals m e power mx and y double prime equals m square e power mx. Let's substitute these values back into the equation given to us. So m square e power mx minus 4 m e power mx plus 4 e to the power mx equals 0, or m square minus 4m plus 4 equals 0, or m minus 2 whole square equals 0, or m equals 2 and 2. So this is a case of repeated roots. We know that when we have real repeated roots, the solutions are y1 equals e power mx, so e power 2x. And to have a linearly independent solution, the easiest way is to multiply it with x. So y2 would equal x e power 2x. These are y1 and y2, and our complementary solution is simply c1y1 plus c2y2, a linear combination of the two. Next, we move on to computing the particular solution, and for calculating or for finding the particular solution, we assume a solution of the form y particular is u1 y1 plus u2 y2, where of course u1 and u2 are functions of x. In this case, the particular solution will be u1 e power 2x plus u2 x e power 2x. We have standard formula for computing these. So u1 prime is w1 by w, u2 prime is w2 by w, and what these w's are, I'll write again. So this is w1 by w, u2 prime is w2 by w, but what are these Wronskians? So the first Wronskian, w, is y1, y2, y1 prime, y2 prime. So here y1 is e power 2x, y2 is x e power 2x, y1 prime will simply be 2 e power 2x, and y2 prime will be e power 2x plus twice x e power 2x. And we compute this determinant. This turns out to be e power 2x times e power 2x plus 2x e power 2x minus twice x e power 4x, and leaves e power 4x. Now, similarly, W1. So the subscript 1 would suggest that we replace the first column with 0 and the given function on the RHS fx and leave the second column of W as it is. So the given function is x plus 1 e power 2x, y2 was x e power 2x, and this will be e power 2x plus 2x e power 2x, and we compute this determinant. The first term is multiplied by 0. We have minus x plus 1 e power 4x. W2 would suggest that we replace the second column of the Wronskian. The first one remains as is. So y1 y1 prime 0 fx. So this will be e power 2x to e power 2x 0 and x plus 1 e power 2x. Here the second term of the determinant is multiplied by 0, and what we are left with is x plus 1 times e power 4x. Now u1 prime was w1 by w. W1 is minus x plus 1 e power 4x by e power 4x, simply minus x square minus x, and u1 thus would be equal to integral of u1 prime with respect to x. So minus x cube by 3 minus x square by 2, and remember we won't have any constants of integration here, that will anyway be taken care of in the final form of the solution. Similarly for the second function u2, so u2 prime would be equal to w2 by w. W2 is x plus 1 e power 4x by e power 4x. So simply x plus 1, thus u2 is integral of u2 prime dx is equal to x square by 2 plus x. Thus our particular solution is u1 y1 plus u2 y2, which is minus x cubed by 3 minus x squared by 2 times y1, which was e power 2x, plus x squared by 2 plus x times x e power 2x. Of course, this can be simplified further, and our general solution thus of the given non-homogeneous ODE will be a combination of the complementary function and the particular solution. So C1 e power 2x plus C2 x e power 2x plus minus x cubed by 3 minus x squared by 2 e power 2x plus x squared by 2 plus x times x e power 2x. This can be simplified further, but that is not really necessary. This is the solution we seek. One more ODE to be solved using the Bayesian parameters. This time it's y double prime minus y equals 1 by x. So we follow the same routine. The general solution will have the complementary function and the particular solution. For the complementary function, we assume the solution y equals e power mx. Start substituting, so m square e power mx minus e power mx equals 0. So because we solve it for the homogeneous equation, which implies that m square minus 1 is 0 or m is equal to plus minus 1. So the y1 is thus e power x and y2 is e power minus x. Our complementary solution is equal to a linear combination of the two, so c1y1 plus c2y2, which is c1 e power x plus c2 e power minus x. Now we move on to more importantly calculating the particular solution, and we assume a form u1 y1 plus u2 y2. We must calculate the three Wronskians, w being y1 y2 y1 prime y2 prime. So e power x, its derivative is again e power x, e power minus x and minus e power minus x. This will give us minus 1 minus 1, which is equal to minus 2. W1, so we replace the first column with 0 and fx and leave the second column as is. Here fx was 1 by x, and this is e power minus x minus e power minus x. First term goes to 0, the second term survives. Similarly for the last one. Here we replace the second column. E power x and e power x, 0 and 1 by x. This is e power x by x. So from the standard formula, we know that u1 prime is equal to w1 by w, which is equal to minus e power minus x by x by minus 2, or e power minus x by 2x. Thus u1 would be the indefinite integral of u1 prime dx. U2 prime will be equal to w2 by w is equal to e power x by minus 2, or e power minus x by minus of e power minus x by 2x, which implies that u2 in this case will be an indefinite integral of u2 prime dx is equal to minus half integral of e power minus x. Sorry, it's plus x here. So e power x by x dx. And it's very interesting to note that these two integrals cannot be simplified further. This is their final form because they are non-elementary types of integrals, and a closed form solution does not really exist. But it is perfectly fine to leave it like this. So our particular solution is u1 y1 plus u2 y2. u1 is e power x, so e power x times half integral e power minus x by x dx plus u2 y2. y2 is e power minus x, so e power minus x by 2 integral e power x by x dx, and our general solution of course is a combination of the complementary function and the particular solution. So c1 e power x plus c2 e power minus x plus e power x by 2 integral e power minus x by x dx minus e power minus x by 2 integral e power x by x dx. This is the solution of the given ODE. Let us first solve the initial value problems using Laplace transforms, and if we have time, we'll come back to some of the easier questions. It also helps to solve the inverse Laplace because that is more involved. Yeah, so let's look at that. So let us find the inverse of Laplace inverse of this given function. So the first step, of course, would be to decompose it into partial fractions. So s square plus s would mean s plus 1, s square plus 1. And we know that this can be decomposed into fractions of the form a by s plus b by s plus 1. And since for the third denominator we have a second order, the numerator would be of the form cs plus d. Had it been of a cubic type polynomial, we would have had something like cs square plus ds plus e and so on. The numerator will be of one order less than the denominator. And A and B are pretty straightforward to compute. We'll compute them using the cover-up method. So A will simply be equal to 2s minus 4 by s plus 1 s square plus 1 evaluated at s equals 0. Since s equals 0 is one of the roots, and this is equal to minus 4 by 1, so minus 4. Similarly, B can be computed as 2s minus 4 by s square plus 1 computed at s equals minus 1, which is the corresponding root. This will turn out to be minus 6 by minus 2, which is equal to 3. C cannot be computed directly by the cover-up method. We'll have to compute it by expanding the terms. So if we were to multiply everything out and preserve just the numerators, what we'll end up with is a times s plus 1, s square plus 1 plus b times s square plus 1 plus cs plus d times s s plus 1 is equal to a s cube plus s square plus 1 plus b times s cube plus s plus c s cube plus cs square plus ds square plus ds. And now we collect the coefficients of all of these terms. So s cube will have a plus b plus c. Square has the coefficients a plus c plus d. S has coefficients a plus b plus d. And the only constant term is a. Now we compare the coefficients of terms on the LHS and RHS. So the coefficient of s cube has to be 0. So a plus b plus c is 0. Or c is equals negative sum of a and b. A and b are already known to us. Minus 4 and 3. Minus 4 plus 3 is minus 1. So c is 1. Again, the coefficient of d s square is 0 as well. So a plus c plus d is 0. or D is equal negative sum of A plus C. A is minus 4, C is 1, minus 4 plus 1 is minus 3, so this is 3. In this, we have decomposed the given function uh, into partial fractions. So 2s minus 4 by s plus 1 s square plus 1 is equal to minus 4 by s plus 3 by s plus 1 plus cs plus d. So 1s plus 3 by s square plus 1. And when we have to compute the Laplace inverse, we try to break these down into recognizable or more standard forms. So the Laplace inverse of this will equal minus 4 Laplace inverse of 1 by s plus 3 Laplace inverse of 1 by s plus 1 plus Laplace inverse of s by s square plus 1, because this term may be mapped to Laplace inverse of the cosine. Uh, Laplace of the cosine has this term. Yeah, so the inverse can be mapped to the cosine. And thrice Laplace inverse of 1 by s square plus 1. And if we refer to the formulae available with us, this will be Laplace of 1 is 1 by s. So Laplace inverse of 1 by s is 1. Laplace of e power at is 1 by s minus a. So this is e power minus t. Laplace transform of cos at is s by s square plus a square. So this is cos 1t. The Laplace transform of sin at is a by s square plus e square. So this is thrice sine of 1t. And this is the required Laplace inverse that we set out to compute. There are more questions, but let us look into the initial value problems first. The others you might do on your own as an exercise. So, how to use Laplace transforms to solve initial value problems? We apply the Laplace transform on the entire equation. So we transform both sides. So L of dy dt plus 3y equals L of 13 sine 2t. Because of the linearity principle, we can separate these terms. So L of dy dt is nothing but y prime plus thrice L of y equals 13 times L of sine 2t. Now remember that the Laplace transform of y power, so the nth derivative of y and derivative of t is s power n f of s minus s power n minus 1 f of 0 minus s power n minus 2 f prime of 0. This goes on till f n minus 1 of 0. So here it's a first order. So the equation we'll end up having is s power 1 y of s minus the value of y at 0 plus thrice y of s equals 13. The Laplace transform of sine at is a by s square plus a square. So this is simply 26 by s square plus 4. Let us substitute the value of y0, which is equal to 6. So ys times s plus 3 minus 6 is equal to 26 by s square plus 4. Ys times s plus 3, we take 6 to the other side, s square plus 4 plus 6, which is equal to 26 plus 6s square plus 24 by s square plus 4, which implies that ys is equal to 6s square plus 50 by s plus 3 into s square plus 4. Now again, to be able to compute the inverse Laplace transform of this RHS, it's best if we break it into partial fractions. So 6s square plus 50 by s plus 3 s square plus 4 can be broken into a partial fraction of the type a by s plus 3 plus this has a quadratic form. So the numerator will be linear. So bs plus c. A can be computed straight away. At s equals minus 3. This will be 9 6 are 54 plus 50 104 by 13, which I believe is 8. B cannot be computed in a straightforward fashion, so we'll have to multiply out the terms and compare the coefficients. A s square plus 4 plus bs plus c times s plus 3 s square plus 4a plus bs square plus 3bs plus cs plus 3c is equal to s square a plus b plus s times 3b plus c plus 4a plus 3c. Now a plus b equals 0. Sorry, a plus b equals 6. And we already have the value of a as 8. So b must be equal to minus 2. Similarly, 3b plus c is 0. So c must equal minus 3b. B is minus 2. So this is 6. Thus, we have the partial fraction form 6s square plus 50 by s plus 3s square plus 4 is equal to 8 by s plus 3 plus minus 2s by s square plus 4 plus 6 by s square plus 4. And now this of course is equal to ys. Now if you have to just compute the inverse of either side, so again just to remember, the way we do it is we transform the entire equation utilizing a Laplace transform, solve the algebraic equation that we thus obtain. We transform the solution back to our original T space, and that gives us the solution of the ODE. square plus 4. Now, the inverse Laplace of ys is simply yt. For 1 by s plus 3, it will be 8 e power minus 3t, because the Laplace of e power at is 1 by s minus a. For s by s square plus 2 square, we have cos of 2t, and again for a by s square plus a square, so we have sine of 2t. This is the necessary solution. I'll just write it out in case it's not clear. So minus 2s by s square plus 4 is equal to minus twice s by s square plus 2 square, and cos 2t will equal s by s square plus 2 square. Similar is the case for, say here we had 6 by s square plus 2 square, or by 4. So this is the same as 3 times twice by s square plus 2 square, and the Laplace of sine of 2t is equal to 2 by s square plus 2 square. This is how the functions were mapped. That was a first order linear differential equation. Now let's look at a second order linear differential equation. Y double prime minus 3y prime plus 2y equals e power minus 40. And we have the values of the system at uh, y of 0, and we also have the first derivative at 0. So of course, first we'll apply Laplace transform to both sides of the equation, and I'll just apply it term-wise because we know of the linearity principle. Now for a y double prime, the terms will be s square y of s minus s y of 0 minus y prime of 0. This was the first set of terms. The second would be, for y prime it will be s y of s minus y of 0 plus twice y of s is equal to the Laplace of e power at is 1 by s minus a. S square ys, y of 0 is 1, so minus s, y prime of 0 is 5, so minus 5 minus 3s y of s, y of 0 is 1, so plus 3 plus twice y of s is equal to 1 by s plus 4. Now this is an algebraic equation, so we collect the terms. Y of s times s square minus 3s plus 2 minus s minus 2 equals 1 by s plus 4. That ys times s square minus 3s plus 2 equals 1 by s plus 4 plus s plus 2 is equal to s plus 4, 1 plus s square plus 4s plus 2s plus 8, or ys is equal to s square plus 6s plus 9 by s plus 4 into S square minus 3s plus 2. Now s square minus 3s plus 2 is itself of the form s minus a s minus b. So s square minus s minus 2s plus 2. So this will be s plus 4 s minus 1 and s minus 2. S square minus 2s minus s plus 2. Yes, that's correct. And we know that once we have a term of this type, we can break it into partial fractions. Again, partial fractions and integration are the recurring themes of this module. And it's best if we are very thorough with our formula and concepts. This can be decomposed into partial fractions of the form a by s minus 1 plus b by s minus 2 plus c by s plus 4. And computing this, these would be straightforward. A is simply square plus 6s plus 9 by s minus 2s plus 4 computed at s equals 1 because y is the root corresponding to a. 1 is the root corresponding to a. This is 1 plus 6, 16 by minus 5 or minus 16 by 5. B is equal to s square plus 6s plus 9 by s minus 1 s plus 4. With this expression evaluated s equals 2 because 2 is the root corresponding to b. This is equal to 4 plus 16 plus 9, 25 by 6 and c is equal to s square plus 6s plus 9 by s minus 1 s minus 2 computed at s equals minus 4. This is 25 minus 24 1 by minus 5 times minus 6 30. So s square plus 6s plus 9 by s minus 1 s minus 2 s plus 4 can be written as minus 16 by 5 by s minus 1 plus 25 by 6 by s minus 2 plus 1 by 30 by s plus 4. And this of course was y of s. Once we have the algebraic solution for y of s, we simply apply the inverse Laplace transform to obtain the solution to our given initial value problem. Laplace inverse of y of s will equal the Laplace inverse of minus 16 by 5 by s minus 1 is the Laplace inverse of 25 by 6 by s minus 2 is the Laplace inverse of 1 by 30 by s plus 4. Laplace inverse of ys is but yt. Here we take the constant out. Laplace inverse of s minus 1 e power at is 1 by s minus a, so this will be e power 1t plus 25 by 6 e power 2t. So all of these are of the exponential forms plus 1 by 30 times e power minus 4t. And this is the solution to the given initial value problem. So we find that Laplace transforms are really useful and really handy for solving this form of equations. If we were to proceed or go about it using, say, our usual methods, it would be quite cumbersome and time consuming. Laplace transform is really coming to the rescue here. Again, just to demonstrate the power of the technique, here we have a third order differential equation, and let's see if this can also be suitably solved. So we have 2 y triple prime plus 3y double prime minus 3y prime minus 2y equals e power minus t, and we have the value of y at 0 is 0, y prime at 0 is 0, and y double prime at 0 is 1. We transform both sides of the equation. As to Laplace transform of y equals the Laplace transform of e power minus t. So, okay, best to bring 2 outside. For the first term, y triple prime, so s cube y of s minus s square y of 0 minus s y prime of 0 minus y double prime of 0 plus trace s square y of s minus s y of 0 minus y prime of 0 minus 3. This is s y of s minus y of 0 minus twice y of s. The RHS is simply 1 by s plus 1, because remember the formula here is Laplace transform of e power at is 1 by s plus a. Sorry, 1 by s minus a. And now we expand these terms. So we have 2s cube y of s minus 2s square y of 0 is 0, y prime of 0 is also 0, y double prime of 0 is 1, plus 3s square y of s minus 3s y of 0 is 0, minus 3 y prime of 0 is also 0, minus 3s y of s plus 3 y of 0 is 0, minus twice y of s is 1 by s plus 1. So these are the terms which are going to 0. We have ys times 2s cube plus 3s square minus 3s minus 2. So these terms are taken care of. Only the constant minus 2 remaining equals 1 by s plus 1, implies that ys times 2s cube plus 3s square minus 3s minus 2 equals 1 by s plus 1 plus 2, which is equal to 1 plus 2s plus 2, so 2s plus 3, which will in turn imply that ys is equal to 2s plus 3 by s plus 1 times 2s cube plus 3s square minus 3s minus 2. Now let's see if we can simplify this cubic polynomial further, whether we can factorize it. Now, the way I solved it is by inspection. We can see that s equals 1 will be a solution. So we can have a component s minus 1, and so I want 2s square. Second term is 3s square, so plus 3s. With 2x cube, this will give me 3s square. 1 minus 3s, so I will have minus 3. And what about the constant? Do I get the constant? This is 2s cube minus 2s square plus 3s square. Okay, so this will be indeed be 5s. So plus 5s square minus 5s, and then I want minus 3s. So plus 2 multiplied by plus 2, then I have plus 2s minus 2. This will turn out to be 2s cube plus 3s square minus 3s minus 2. Yes. So we have been able to isolate one of the factors. This is equal to s minus 1 times 2s square plus 5s plus 2. Let's see if we can do better. So this is 2s square plus, so if I take s common, 2s plus 5 2s square plus 2s plus 3s plus 2. What can be a good way to break this? Two s square plus 3s plus 2s plus 2. Or if we just take, oh, we can find its roots directly by quadratic formula. Why am I even bothering with this? Really sorry. So for 2s square plus 5s plus 2, the roots are s equals minus 5 plus minus under root b square minus 4 ac 4 into 2 into 2 by twice a. So this minus 5 plus minus 25 minus 16 plus 9 plus minus 3 by 4, or s is equal to minus 5 plus minus 5 plus 3 is minus 2 by 4 is minus half, and minus 5 minus 3 is minus 8 by 4 is minus 2. So the roots are indeed s minus 1, s plus half, and s plus 2. Therefore, ys is equal to 2s plus 3 by s plus 1, s minus 1, s plus half, and s plus 2. Now again, we have to break this into partial fractions. I will leave that to you as an exercise because I have done it many times today already. But what I can tell you is that the final form of this will look something like half of 1 by s plus 1 plus 5 by 18 times of 1 by s minus 1. Of course, it's a straightforward exercise if you use the cover up method. Minus 8 by 9 times 1 by s plus half plus 1 by 9 times 1 by s plus 2. And to get back our solution in the t domain, we apply the Laplace inverse to either side. Plus half plus 1 by 9 times Laplace inverse of 1 by s plus 2. And what we end up with is y of t equals half e power minus t plus 5 by 18 times e power t minus 8 by 9 times e power minus t by 2 plus 1 by 9 times e power minus 2t. And this is the solution to the given initial value problem. And we saw that how utilizing Laplace transforms, we easily solved the given initial value problems by converting them basically into algebraic equations, which we then had to factorize, in most cases break into partial fractions, and then simply invert them back to t space term by term. There are a couple more questions which may serve as a good revision exercise before you attempt the assignments. So you may solve them yourself. They're rather straightforward, just that it helps to practice. And that is all the content I had for today. So Anirudh, did you already attempt the quiz for this week? Anirudh, are you here? Okay, maybe not. So thanks for tuning in to week 4 of the live sessions for computational science and engineering. I am Sourav Goswami from IIT Bombay, and I look forward to meeting you again next week. Thank you.